Yeah, so let's see. Right. So basically, we've been looking at exponentials. When we did the sorry, when we did the lines of code model for effort months, basically the size of the coding project in thousands of lines raised to the power of n is an exponential model. When we do present value is 1 plus I to the n time, future value times the present value. That's an exponential model because we're taking something, whether it's ADSI to the power of n. We're taking something, 1 plus the interest rate, to the power of n. And, up till now we've thought of n as being a fixed number. So what happens after 10 years, or what happens after 20 years? And we think of, in this particular case, KDSI as being the variable, so that the length of the project will tell us how long it will take, and the constant multiplier and the n here. So n is not years. So here with the money, n was years, but here n was just some exponential that fitted in the model. So when we're doing this lines of code thing, the KDSI was the thing that changed. We could change from 5,000 to 10,000 to 15,000 lines of code. And so the model of this was a times x to the n, where x is varying. And this is what's known as a power function, because the x is varying and we've got a power of x. On the other hand, this future value, present value thing, it looks very, very similar, but really what we're interested in here is the interest rate is fixed, the present value is fixed, and we're thinking about what happens in 1 year, 2 years, 3 years, 4 years, 5 years. So in a sense, the power is changing. So in that case, what is changing is the number of years. And we're asking ourselves what happens after 2 or 5 or 10 years. So the compound interest formula is a constant times a base to the power of x, and the x is varying. Okay, so you put in a value of x, a number of years, and what comes out is the future value. Whereas in this lines of code model, what goes in is the size of the programming project, the number of lines, and we raise that to a power to give out the effort months. So when we've got this, we've known as an exponential function. So they almost look the same, but there is quite a big difference. So down here, power functions. So remember that x is varying, or if you like, changing. So x is varying or changing. If the changing thing is raised to a fixed power, we have a power function. If, on the other hand, we've got a fixed base raised to a changing power, that's when we have this exponential function. And just down here, I talked about b as being the base and the power being the exponent. So let's have a look at something like 2 to the x. So remember here, x is going in, y is coming out, but we're doing 2 to the power of x. So this is an exponential function. Let's do the easy one first. 2 to the power of 0. 2 to the power of 0 is 1. 2 to the power of 1 is, well, that's just 2. 2 to the power of 2, 2 squared is 4. 2 cubed is 8, 2 to the power of 4 is 16, 2 to the power of 5 is 32. So you can see that going from here to here to here to here, we're doubling at each step. So 2 ones are 2, double gives you 4, double gives you 8. So we're just multiplying by the 2 with each step. Well, if we're multiplying by 2, as we go from 0 to 1, 1 to 2, etc., that also means we're halving if we go backwards. So if we go backwards from x equals 5 to x equals 4, we halve from 32 to 16, 16 to 8, 4 to 2 to 1. So what happens when we go from x equals 0 to x equals minus 1? Well, we're going to get 2 to the minus 1. Now, there's two ways you can think of this. They're both equivalent, and you should think about it in both ways. If I double going to the right, then I halve going to the left. So half of 2 is 1. Half of 1 is a half. Or the other way to think of it is 2 to the power of minus 1 is, use our rules of exponent, we've got negative in the exponent, so we make it 1 over, and 2 to the 1, where negative 1 becomes positive 1, and we take the reciprocal. Okay. Go back another step. A half of a half is a quarter when we go from x minus 1 to x minus 2. So you can think of this as 2 to the minus 2 is 1 quarter, or 2 to the minus 2 is, we've got negative in the exponent, so we make it 1 over 2 to the positive 2. So the negative 2 becomes a positive 2, and we take the reciprocal. And go back another step, half a quarter is an 8. So as x is going from minus 3 to minus 2, you see it's pretty small, gets a bit bigger, and then all of a sudden it's getting fairly big. Then 64, 128, 256, 512, 1024, 2048, 4096, and so on. And this doubling, doubling an 8 to a quarter is not very big. Doubling a quarter to a half, again, not very big. Doubling a half to 1 is not very big. Doubling 1 to 2, well, we're still pretty small. Doubling again, we've got 4. Doubling again, we've got 8. It's still not very, we've done several steps and we haven't gotten to a very big number. But double again, 16. Double again, 32. Double again, 64. Double again, 128. Double again, 256. All of a sudden we're starting to get bigger and bigger numbers, but they're rapidly getting bigger. So here they were getting bigger, but not very fast. Out here, they're going to get bigger, but really quite a lot faster. And what I was trying to do before was graph this and not rely on this. So here's the graph. Along the x-axis, we've got the exponent and 2 to that exponent along the y-axis. So when we've got minus 3, that was 1/8, that's 1/16, 1/32, and so on. And you can see that this is really very, very small. It doubles as you go up here, and it grows more quickly with each step once your x's get somewhat bigger. So by the time you get to 2 to the 20, so 2 to the 10, now it's 1024. 2 to the 20, though, is well over 1 million. Let's see if I can get this. So 2 to the power of 10 is 1024, what we expect. 2 to the power of 20 is 1,400,000. 48,576. 2 to the power of 30 is quite big. So that's, let's see, 1,073,741,000. So this is 1 million, 2 to the 20, but 2 to the 30 is 1 billion. Basically, it's 1,000 times, well, it's 1,024 times bigger. So when we went from 2 to the 1 to 2 to the 10, we went from 1 to 1,024. We moved from 2 to the 10 to 2 to the 20, we have 1,024 times 1,024. When we go from 2 to the 20 to 2 to the 30, that's multiplying by 1,000 again. So these numbers are going to get big pretty rapidly. Let's see if I can plot this. So here's a plot. Why this is not what's happening here. So I don't know quite why this is stopping at 8. This is really weird. Let's go to 20. Let's see if I can trick it. Okay, so 2 to the 30, you can see 2 to the 30 is 1.2 times 10 to the 8, so pretty big number. And you can see how here the rate of increase down here, the rate of increase is pretty small, but here it's getting bigger very, very rapidly. So very, very steep increase. Again, this is exactly what's happening with the this virus. So there's nothing particularly remarkable about 2 to the x. If we've got any base which is bigger than 1, y equals b to the x is going to have the same general shape as 2 to the x. Okay, so if we're looking at 3.2, 3.2 to the 0 is going to be 3.2. That's what it's going to be 1. Sorry. So if you look at 3.2 to the power of 0 was 1. So that's why it hits 1 on the y-axis when x equals 0. Same thing here. 2 to the 0 is also 1, so that actually was 1 just in there. For positive x, the exponential gets steep very quickly. For negative x, the function as x gets more and more negative, so big in the negative direction, but 3.2 to the x gets closer and closer to 0. Most of the time, we're just going to be interested in this area where x is positive. We're not going to be interested in when x is negative, because that's what happens for most reasonable problems that we will face. So if we, no, I don't have blue and red here, but I can do this. If we look at x squared in green, okay, x squared, remember x squared normally looks like, if we plot it normally, it looks something like that. Well, if we plot it together with 2 to the x, we see this dramatic difference. So even just with x going up to 10, x squared, 10 squared is 100, so there's 100. 2 to the 10 is 1,024. You see this really big difference. So imagine, so this is our x squared. 2 to the x is basically looking like this. It goes, zoop, goes up really, really quickly. And if we expand this out, flatten it down, x squared, that's still curving up, but very, very gently compared to the exponential. And really, there's nothing particularly important about 2 to the x and x squared. This is a feature of exponential, so we call this exponential growth. Exponential growth always overtakes power growth. So we think of this as being a power, we've got the power of 2 versus exponential. Exponentials always beat power. So that's really what this slide is saying. The function 2 to the x overpowers x squared. And that's because 2 is bigger than 1. Same thing with this. Even if I had 1.01 to the power of x, eventually that will become greater than x squared. It'll even become greater than x to the 100. So x to the 100 might beat 1.01 to the x initially, but eventually 1.01 to the x will just beat. So it might look something like this. X to the 100 might go up like this. 1.01 to the x might, so this is x to the 100. 1.01 to the x might be slow for a while, but then it gets to a point where all of a sudden it just shoots up, whereas the x to the 100 just keeps on going at a much gentler rate. So eventually 1.01 to the x will beat x to the 100. Mightn't be initially, but it will eventually. Yeah, this is, if you can see these in color, sorry, I only printed in black and white, but this is 2 to the x, and this is x to the 74. And you can see that x to the 74 is just slightly above 2 to the x. So there's x to the 74, and there's 2 to the x. So x to the 74 is beating x squared up till about x equals 700. But then all of a sudden, it happens very, very dramatically. Once you get beyond this point, 2 to the x rapidly increases, whereas x to the 74 sort of moseys along quite gently. And again, it's exactly this that the epidemiologists wanted to avoid with this current virus, because if we let it go away, even with 1.01 to the x, you'll get this rapid increase. And the difference is really very much bigger. That I have to say, that is not an intuitive result. This, because your temptation is, well, 74 is much bigger than 2. So x to the 74 is a pretty big number. And yes, it is a pretty big number up to about 700. But 2 to the x is an even bigger number once you get to 705. And it's an absolutely ginormous number by the time you get to 710. And even to 715, the difference is sort of unimaginably large compared to the x to the 74. So in a sense, this is really very non-intuitive material. So when we were doing square roots, we're also doing exponentials, in a sense, or in every sense. So when we said something like 16 equals 4 squared, we could turn that around and say, well, what is the square root of 16? Well, 1 square root of 16 is 4. In fact, 4 is the positive square root. Don't forget the bent tick symbol means take the positive square root. And we could write, instead of 16 equals 4 squared, we could write 4 equals 16 to the half. And the relationship is that the half is the reciprocal of the 2 there. And remember how we justified this. 16 to the half times 16 to the half is 16 to the half plus a half, which is 16 to the 1. And what's 16 to the 1? That's 16. So something times itself gives you 16. What do we have? Well, we must have the square root of 16, or the positive square root of 16. So what we're saying here is that these two statements, 16 equals 4 squared and 4 equals 16 to the half, are basically equivalent. They mean the same thing. If you know one, you know the other. If I tell you 4 equals 16 to the half, you can tell me straight away 4 squared equals 16. If you tell me 16 equals 4 squared, I can tell you straight away, well, 4 is 16 to the power of half. And exactly the same thing with this cubes. So if I know that 8 equals 2 cubed, straight away, what's the reciprocal of 3? 1/3. So 8 for that 1 over 3 gives me 2. And again, 8 to the 1/3 times 8 to the 1/3 times 8 to the 1/3 is what? It's 8 to the 1/3 plus 1/3 plus 1/3 is 8 to the 1, which is 8. Which is 8. So what times itself 3 times gives you 8? Well, it must be the cube root of 8. In each case, so in this case we know something about a power statement. So 2 to the 3 is 8. 4 squared is 16. So those are both to do with powers. And we're converting this into something about the base of the power. So the base is 2, power is 3. Over here, we're saying the base 2 is 8 to the 1/3. So the base of this is that power to the 1/3. Same thing here. 16 is 4 squared. That base of 4 we can rewrite as the power to some exponent. So this power, this 16 is 4 squared, that's the power. So base exponent to power, power to something gives us the base. And there's yet another way of writing all that information. It's these things called logarithms. So if we start off with 16 equals 4 squared, another way of writing that using logarithms is we say the exponent 2 is the logarithm of the base is 4, of 16. So 4 is the base, and you read it as 2 is log base 4 of 16, or log of 16 to the base 4. What this is asking, so if I asked you, if I said log base 4 of 16 is what you're asking yourself is 2 to what power, so, 4 to what power that is equal to 16. And since you know that, since you know that 4 squared is 16, you know that log base 4 of 16 is 2. Same thing as if I asked you, here I'll do it this way, log base 2 of 8 is what? So you ask yourself, 2, the base, to what power, the unknown, is 8. Now you know from what we've just done that 2 to the power of 3 2 to the power of 3 is 8, so we know log base 2 of 8 is 3. Basically, what we're doing is rewriting these statements about powers in terms of statements about these logarithms. I don't quite know exactly what logarithm means, but it's just a different way of expressing the same information. So now we have this. B is the base, y is the exponent, x is whatever b to the y is. So we can always rewrite that as log base b of x is equal to y. So log base b of x is equal to y. Log of the base, log to the base of that value is that exponential, or is that exponent. And you're asking what, so just like I said here, what power of 4 gives me 2? What power of 4 gives me 16? The power of 2. What power of 2 gives me 8? Power of 3. So let's, log of 16, base 4 is 2. Is 4 to what power gives me 16? 2. That's what this is happening. What's happening here? What power of 4 do I have to raise it to give me 16? Well, the answer is 2. That's so log of base 4 of 16 is 2. And the important thing is that the base and the power both have to be greater than 1. And also the base has to be not equal to 1. So if I ask you, log base 10 equals 100, you say to yourself mentally, 10 to what power gives me 100? You know, 10 to the 1 gives you 10, 10 squared is 100. Oh, okay, so 10 squared is 100. So log base 10 of 100 is 2. So this statement and this statement are exactly equivalent. I mean, there's no extra information in it. And really quickly, we can do some calculations. Okay, we can do some calculations. I ask you log base 2 of 16. You say to yourself, 2 to what power is 16? And you know the 2 to the 4 is 16. So you rewrite it as log base 2 of 16 is basically 4. I mean, you could put in this extra step. Because 16 is 2 to the 4, you could rewrite 16 as 2 to the 4 and say log base 2 of 2 to the 4 is 4. So see this base here, 2, and that base there, 2 are the same. So when you ask log of this base of that number here, I just get that exponent. Now this one's a bit trickier, but it is important. So log base 4 of 2. 4 to what power gives me 2? And this is where you've got to apply a bit of lateral thinking, because 4 to the power of 1 is 4. 4 squared is 16, so they're not going to be any good. 4 to the 0 is 1. So if you think 4 to the 0 is 1, 4 to the 1 is 4, and we're after 2. Well, the exponent must be somewhere between 0 and 1. And then you think, oh, I remember, the square root of 4 is 2. How do I write square roots? 4 to the power of half. So log base 4 of 2 must be a half. Why? Because 4 to the power of half is 2. So in the exam, or later on if you do a test, and it asks you to justify something like log base 4 of 2 as a half, you want to tell me the reason is 4 to the power of a half is 2. And all you're doing is rewriting this information in this log form. Log base 10 of 1 over 10. So 10 to the watt power is 1 over 10, where you know that 10 to the power of minus 1 is 1 over 10. So that log has to be minus 1. Okay, this one's an odd one. Log base 5.47 of this number. So you say to yourself, 5.47, that's the base, to what power is equal to this number? Well, that number is 5.47 squared. So 5.47 to what power is 5.47 squared? Oh, that has to be 2. So we've got straight away 2. Now, let's see. Okay, suppose we've just got 2 little ones to go. So suppose I'll give you a couple of minutes or 1 minute to work out log base 10 of 0.001. I'll time it. I'll give you 30 seconds. That was a bit more than 30 seconds. So the trick is you've got 10 to what power is 0.001. And the trick here is to write this as a power. So this is actually 1 over, we'll do it this way, 1 over 1,000. Okay, so 1 over 10 would be 0.1, 1 over 100 is 0.01, 1 over 1,000 is 0.001. What's 1,000? That's 10 cubed. And how can we write this as a power of something? Well, 1 over 10 cubed is 10 to the minus 3. So the logarithm is minus 3. Okay, if I ask you that one, that's a little bit trickier. Again, I'll give you 45 seconds for that one. Okay, I think that was a bit over 45 seconds. So again, the idea is that we want to write 3 to, so we've got a base 3. 3 to what power is square root of 27? So there's probably a little bit of work there. We want to run it. So the work here is that we can write out 27 as a power of 3 to begin with. So So 27 is a power of 3. It's actually 3 cubed. So we can write root 27 is square root of 3 cubed. And then we say, oh, I remember what to do with square roots. Simply power to the half. So 3 cubed is 27. So the power of a half is, that's a square root. What do we do with the power of a power? We multiply it, so 3 times a half is 3 halves. So now we've got root 27 is actually 3 to the power of 3 halves, and that straight away tells you that log base 3 of root 27 is the 3 halves. And we've basically done. Okay, so that's lecture 16. Stop sharing it for a ticket. Now I just saw somebody was asking via the chat, if I can find it. There's a chat. Yeah. So somebody was asking via the chat about the exam. So again, I've already sent out what it will look like. But effectively, you've got 24 hours to complete it. So when you write to me and say, I'd like to start the exam, I will send it to you, and then you have 24 hours. You might pick up, I might send it to you at 9 a.m. on Monday morning, and then you have 24 hours until 9 a.m. on Tuesday morning to get it back to me. Now, I'm assuming, I'm designing it, so I should say, I'm designing it so that you really only need to take 3 hours over it. So it'll be just like an ordinary end-of-year exam in terms of the total amount of length, but you actually have the whole 24 hours to do it. So you can work on it for an hour, go away, think about something else, and then come back to it. So you can really think of it as a bit of a mini assignment that's just 24 hours in length. But I'm designing it that, if I send it to you at 9 a.m. and you sat down and just worked on nothing else for 3 hours, you should complete it by 12. But then you've got the extra time to get it into me or to think about it a little bit more carefully. So yeah, you can do a couple of questions, have a few hours break, and then come back to it. You don't have to sit down for the whole thing. As I said, I've done those myself when I was a lad. I really quite enjoyed them. It meant that if I looked at a question, I thought, oh, I don't know how to do that. I just left it for a while and did something else, came back, maybe had a bit of lunch, and then started on the question I didn't know how to do. So it's a little bit more relaxing in one way. One thing I would suggest is that you don't work on it solidly for 24 hours. I mean, I think that would defeat the purpose and just cause a lot more stress if you tried to work on it solidly, even for 10 hours. But I think 3 hours really should be plenty sufficient. And then if there are just bits and pieces to mop up, well, you've got the extra time. It also means that you have, if there are internet problems, then you're not stressed out by trying to get it back because the internet broke or your computer failed or something. You've got a little bit of time to sort those things out because they do happen. And so, are there any questions that you want to ask? So there is one more thing I need to say, and it's about tomorrow. Everybody realise that tomorrow is a holiday. Okay, one nodding. So tomorrow is a holiday. Oh, today's Thursday, isn't it? Yeah. So tomorrow is a holiday, Good Friday, and then Monday also is a public holiday. Tuesday is an official university holiday, so strictly speaking, none of us are doing any work, as in, I mean, ordinarily we wouldn't be attending our office, but we're not attending our offices anyway. However, normally tomorrow we would have a tutorial. So what I'm suggesting is that even though next week is as in Wednesday, Thursday, Friday, is an official break in the university, just meaning no classes are being held. What I'll do is maybe make 1 or 2 hours on Wednesday morning a consultation time. So if you just want to, I'll set up Zoom And if you want to just reply and ask a question, I can help you there and then. So, not necessarily too early in the morning, maybe 10 o'clock. Have one day we can sleep in a little bit. So maybe Wednesday 9 till 10 or thereabouts, just as a consultation. And if you've got any problems particularly about the prac or about the assignment that I'm about to send out, then you can drop in that I'll send an LMS message about it. Okay, so I think that's enough talking from me. Any questions from you?
So how much time are we supposed to have for this assignment that you're about to put out?
Yeah.
Also, your microphone appears to be glitching a bit too.
Sorry?
Something seems to be up with it.
Yeah, okay. Actually, if you could let me know, please, because I have no feedback with these things, so I really can't tell. I'm speaking to the ether. I'm assuming everybody can hear or something. I think the only thing that might be happening is I discovered yesterday I've got a metal zip on my jumper, and perhaps the microphone is rubbing against it. So I'm sorry about that. Also, the assignment, yes, I'll basically give you a week, which probably in practice means until Monday of the week that we get back, so Monday week. But again, it shouldn't really take you more than an hour or two, because it's based on what you would have done as your 1 hour in-class test. And it is only worth 10%. It's really just to get a bit of feedback. Anything that I'll do is ask maybe, which is where I've been a bit stuck on, asking a question that involves a little bit more writing, but as in more like a little essay writing than I would normally do in an in-class test. But it won't be a major essay. It's like a paragraph or two, rather than War and Peace or something like that. 1 hour, hour and a half tops for an assignment to replace the test. And as I said, for the other two tests, I'll see if we can do something with these online quizzes that so many of us have been experimenting with. Have you found out what is happening in your IT subjects as far as the exams go? Is anybody giving you any?
No.
No, okay. I think I haven't told you yet. It might be worthwhile just flicking your other lecturers an email saying what's happening with the final exam, because we're supposed to be letting you know pretty soon so that you don't get stressed out about it. I mean, again, this is all new to everybody, but every university is in the same boat with trying to figure out what to do with exams online. So mathematics is particularly difficult because of the writing aspect of it. It's not so bad in maths for IT, but you can imagine in some of the other subjects where the writing or the symbols are very technical. Basically, you can't do it on Word in any sensible fashion. And there's no other easy, well, there is an easier, there's something called LaTeX, but not everybody's got access to it. Whereas everybody can write on paper and at least scan. So we can look up between now and whenever ways of scanning, at least using your phone. So one of the Google apps, there are other apps available for iPhones, I think, and most of them work pretty well. Or if you've got a printer that does scanning, that'd be okay as well. The main thing is not to have files that are too big, and not to have photos, which tend to be pretty big as well. So something that converts a photo into a PDF file is ideal.
I think Officeworks can do scanning as well.
Yes, Officeworks can do scanning. I think that perhaps save that one up as a last resort, only because you have to go in physically in there. and you probably want to avoid being out as much as possible these days. But yes, that would be an absolute last resort, and you've certainly got the 24 hours to organise that. But I think most people have phones, and that would, look for an app that converts photos to PDFs. There's a couple of good ones out there, including the Google one. Okay, any last-minute questions? Yes, no, silences are sent again. I've muted you, so okay, so look out for the assignment. Look out for the message about the consultation hour next week. Let's say Wednesday morning-ish, mid-morning, 10-ish, and then we'll meet again as a group the week after next. Okay, so have a good break. Work out on your other subjects.
Thank you.
And enjoy yourselves the next few days.
You too.
Yep.
Hopefully you can get some rest.
Yes, well, I had yesterday, I was in, I think, 5 hours of Zoom meetings, which is exceedingly tiring. It's good in the sense that it's better than, being able to give classes or be in meetings at all is an advantage. I do find that classes in particular, depending on how they go, are actually more tiring than standing with a class in a classroom. But we'll survive.
Yeah.
Anyway, good luck. We'll see you in a week or so.
Thank you.
I'll end up here. Cheers. Bye.